Aloha and good evening or good morning, wherever you are or whenever you're watching this. Aloha. My name is DC, and we'd like to welcome you to the Journey Through the Universe Public Talk. I'm DC from B97, B93. It's a radio station here in Hilo, Hawaii, where I'm at. In fact, I am in our studios right now and so excited to be a part of tonight's talk because we're going to be sharing in some extraordinary details about the exciting revolution of ground-based astronomy. Of course, it's not for me, but I am surrounded by some amazing people who have some great information, who have their fingers on the pulses of the latest technologies. We're also going to do a little bit of stargazing here a little bit later on. So we would like to officially welcome you to tonight's Journey Through the Universe public talk. And before we get down to meeting our main guest here tonight, I'd like to go around and introduce some of the folks you may see all around your screen here. I want to say, first of all, probably to the person on the screen who's the coldest, Jamaica Marshall. Hi, Jamaica. How are you doing up there? You are live from Mauna Kea here on the Big Island. How are you doing? Are you staying warm?
Thank you, DC. Yes, actually, I just stepped from inside of the visitor information station here at the 9,200 foot level on Mauna Kea, where it's very nice and toasty. So my fingers are actually working right now. And yes, I am so pleased to be joining you all today. As you can see, it is still pretty light outside. The sun went down a bit ago. And so I am having my setup already going, and we'll be joining y'all in about 45 or 50 minutes for some live stargazing along with my colleague, Robert Sparks.
All right. Thank you, Jamaica. And let's say we have Rob here, Rob Sparks, who is live from Tucson, Arizona. Hi, Rob. How's everything in Tucson here this evening?
Pretty good, DC. It's not quite as cold there. It's probably cold by Hawaii standards. I'm probably in the mid 50s here at this time of night. No wind, so it's very comfortable out. And I'm just in a parking lot here, so you're not missing much with the view behind me.
Nice. Well, you look good, sir. You look good. Also, let's see, who else do I want to introduce you? I do want to make sure that we mention our guest speaker that we're going to talk to here in just a few minutes, because where he's at, it's morning time, and we want to say good morning to Lars Lindberg Christensen, live from Munich, Germany, where he's escaping the pandemic. Lars, good morning to you. How are you doing, sir?
Good morning, good evening, DC.
Nice to see you, Lars. We're excited to talk about what you've got to talk about. Some amazing things. So we're looking forward to that. If you don't mind, before we jump into our discussion, Lars, I want to say hi to a few other folks that are joining us here today. And please jump in if you'd like, folks. Janice Harvey is here. And Janice is really, I want to call her the evangelist of Journey Through the Universe here on Hawaii Island. We've worked together for many years. And Janice, you do just an amazing job of getting the word out and helping some of the young minds understand science. Thank you so much for joining us, and thank you for making this happen.
Oh, DC, thank you so much for allowing us here today and to be part of this program. And just briefly, just so I can just share with the audience that's joining us, Journey Through the Universe is a program that the observatories on Mauna Kea, NORLAB, Gemini Observatory have been going into our classrooms for 17 years. And on an average year, we see about 8,000 students, and we're teaching them about astronomy and science. And we're just so privileged to be able to work with our local Department of Education. This year, however, because of the pandemic, we had to kind of, readjust. So we are having all of our classrooms virtually. And I must say, we're going to be seeing about 6,000 students this week. 6,000. And tonight is just one of our special events. I can't thank you enough for emceeing this event. And my gosh, I wait until you hear Lars speak. And so, DC, I'm going to turn it back to you. Have a wonderful evening, and thank KWXX, New West Broadcasting, for being part of our evening.
Thank you so much, Janice. It's our pleasure. Yes, and I should mention, besides B97, B93, you're also part of KWXX and KPUA, New West Broadcasting. My awesome boss, Chris Leonard, who is a man who's working constantly. He's also a coach. I don't know how he fits all his activities into his day, but he's also a volleyball coach at the University of Hawaii at Hilo. So he can't be with us tonight. So, but boss, thanks for helping make this happen and making this happen. Peter, can we say hi to you real fast? We have Peter Michaud from Gemini, a man that I've known for, gosh, almost about 20 years now. I had the wonderful opportunity in 2003 to go up to Gemini. Peter, great to see you. How's everything with you, sir?
Thank you, DC. It's great. Can't wait to hear the lecture tonight. And again, we so appreciate you facilitating this for us tonight and keeping things on track. So thanks again.
Hey, it's my pleasure. Thanks, Peter. Great to see you, man. You just never age. You never age. All right. Well, without further ado, we would like to get right into our fun this evening by introducing to you our main guest, who you just met here a few minutes ago. He's the head of communications education and engagement from the National Science Foundation's NORLab, all the way from Munich, Germany. I want to say good morning to Mr. Lars Lindberg Christensen. Lars, good to see you again, and good morning. And Lars, I want to apologize in advance. If I say Lars Christian Andersen, please correct me, okay? I don't know why I want to say that. Lars Lindberg Christensen, okay? Sorry about that.
Easy.
And
I'm gonna jump right in and share my screen here. So we're gonna talk about astronomy today, stars and galaxies and telescopes, about something new that's happening, which is, I think, quite the next step. Before we start talking about all the technology, I think we should start with the big questions that we have in astronomy. And I think it can be synthesized to three main big questions. And number one is, where did we come from? So that is really one of the biggest mysteries. What happened since Big Bang 13.8 billion years ago, and then up until today? Now, back then, when the universe expanded very, very rapidly, it was a fairly even soup of gas. And then we look around us today and we see this wondrous, diverse, and complex world out there in the universe with stars and planets and galaxies. So in between, what happened is that the stars, they were functioning as recycling factories. They were upscaling lighter elements like hydrogen or helium to heavier ones like carbon or silicon, even up to iron, which also, by the way, means that we actually have stardust in our bodies. The iron in our blood comes from this recycling in stars. And heavier elements like, for instance, uranium or plutonium that we all know about, they were actually formed in supernova explosions. So there's been this increasing upscaling of elements in the universe. But there are many details in this that we don't actually understand. We don't understand how black holes play into all of this, and how these galaxies form and grow. Lots of mysteries are hidden there. And the second big mystery, I would say, is, what is the universe composed of? That's a whopper, actually, because it turns out that the normal matter that we know and we are composed of, atoms, that's only 5%. So all planets, all people, all stars, all galaxies is just 5% of the matter in the universe. 95% is mysterious, and we don't know what it is. So we've invented these two names for it. That's something scientists do when they don't know stuff. They call it funny names. And 26% is something we call dark matter, and around 69% is something we call dark energy.
now, I don't know about you, but don't those sound like great monster drink names? Dark energy, dark matter. I'm sorry, for those long nights on Mauna Kea,
That's right. And you could also say,
I get. I'm sorry. Go ahead.
No, you go.
I guess. Well, I was. Again, I'm going to be asking the regular average Joe questions, but I mean, how do we know that these there are these unknown substances if we can't see them? I mean, how do we know for sure it's dark matter? What is it? How do we know? What's the? I'm sure there's the science behind that.
That's a great question, and you could ask the same about black holes and all of this, right? And it is tricky because in astronomy, we can only look out in the universe. We can't go into the lab like a biologist can and take samples and, dissect things. But we do have the light. And I can show you an example. So if you look out for instance, at a cluster of galaxies, that's these yellow fellas that you can see, the big ones here. So these are sort of nearby objects in the more local universe. Then if you look closely at this kind of picture, you can see that there is something odd, right? And anyone can see that. And in fact, the Gemini Observatory director, Jen Lotz, she designed a program to look at these clusters. So she basically took this picture with Hubble together with her co-workers, one of my favorite images of all time. And everyone can see there is something funky, right? You see these bananas, distorted galaxies. And what that is, in fact, is that the light from background galaxies are passing by this big cluster of yellow galaxies, and the light is getting distorted on the way. And that's physics. So Einstein, he noted this general theory of relativity that said that matter can distort space-time. And that basically means that light is passing by and getting bent by the mass of those intervening yellow galaxies and getting contorted into these shapes that you can see in this picture. It's almost like looking through a lens that's not perfect, or like the bottom of a bottle or something like that. And you can then kind of count the galaxies both in the foreground and background, and then you can actually make a map of the matter, not just the matter that you can see. And that's how it appears that there is at least 10 times the matter that we can see in the cluster. So that's why we know that there is all this dark matter in an object like this. Or maybe an even more, I would say almost psychedelic example is this one. So I'm going to try to explode your brain, DC, because this one is also one of my favorite images. So in this picture, you see some galaxies. It's in fact two clusters of galaxies that have collided at some point in the past. And then you can kind of look at the distribution of the dark matter with this method that I just mentioned, with the distortions of the background galaxies. And that's what's colored blue. So that's the dark matter. And then with the Chandra X-ray Observatory from NASA, scientists have mapped the matter, the normal matter that emits light, which is of course stars and galaxies, but also some hot gas in these clusters, and that's in pink. And what you can see is that the normal matter has been distorted. It's almost like a plane, going supersonic. It has a shock wave or a bullet in a sense. So the pink normal matter has been distorted in this collision between the galaxies, as you would expect. But the dark matter in blue has passed through completely unhindered. So that gives us a clue that dark matter is not like normal matter. It doesn't actually interact with normal matter, but just passes through. And that's really dumbfounding. It's just like one of these cases where a photo is saying more than 1,000 words. But coming back to those three big questions, so the third one is kind of transcending astronomy and becomes philosophy, I would say. It's arguably the biggest question of science, maybe even religion. Are we alone? And there's so much to be said about this, but we can also talk more about that in the Q&A session a bit later. So I want to start back in time, thousands of years ago in antiquity. There were astronomers back then. In fact, astronomy is the oldest of natural sciences, we say proudly. Astronomers back then, they looked at the stars and they looked at the moving stars. They called them, in fact, what we call planets today. And they mapped them and found out how to, when to sow, when to harvest, and it gave them clues to those kinds of things. were very important people back then in terms of timekeeping and many other things. They could even predict things like solar eclipses. And then up through time, people were using those visual observations. They were looking out in the sky. So DC, do you have any idea what this may be?
It looks like a, I don't know. It looks like they clean things up around Stonehenge. Stonehenge is really nice. I don't know. Is that a farm somewhere in France? I guess it looks kind of like a farm. I give up.
Yeah, almost. So this is
That's all
where it all began in many ways. This is where sort of modern astronomy started. This is the island of Wien in one of the most beautiful countries of them all. I may be a bit biased because it's my home country, Denmark. Tycho Brahe, he was an astronomer back then, many hundred years ago, and he looked out with instruments standing in this garden-like structure at the sky. But what he did was he was meticulously noting down everything that was going on with the planets. And with that, he kind of started the whole scientific method where you use facts to reason and to prove or disprove theories, and then you go back and observe some more. So this took place and was working very well for hundreds of years. And then around 1609 or maybe 8, in the Netherlands, the telescope was invented. And with that, Galileo started then observing the sky. And he looked at planets, the moon, even the sun. In fact, he went blind because he looked at the sun. So that's a really, really bad idea. You should not look at the sun with a telescope. But apart from that, he did amazing discoveries.
Yeah. Wow, fascinating. Fascinating.
And then, the telescopes got more and more sophisticated, right? This is a picture from around 200 years ago, or so sort of 150 years ago. And telescopes became state of the art, and astronomers were genuinely looking through a telescope.
Right, which I think is sort of, isn't that still the image? Still, people still think that that's what you do. You get on telescopes, you look up. Is it, or is that? I guess that's it's different now, right? I guess that's my question.
It is. Back then they were looking at the sky with the eyes, and they were making drawings. Like I'm not sure you can see this one here, but that's a drawing of it. In fact, the Orion Nebula in a book from 150 years ago, which was how they registered light back then. And the eye is an amazing invention of nature, one of the most sophisticated things that nature or divine powers have made. We have these sensory cells. We have light-sensitive rods and color-sensitive cones in the eye, and we can really see a ton, and we can adapt and do all that. But in terms of science, it's a little bit tricky because it's hard to register light precisely, right? We have subjectivity, and what we need is objectivity. So around came then the 1850s with the invention of the photograph, and very soon after, astronomers started taking pictures of the stars, and they did that using glass plates. So this was how photographs were made back then. In around that time, 1850s, and a good several dozens of years further ahead.
This picture is from 1850. This one right here. This is how they did it. Huh?
So this one is probably several tens of years later. So the glass plates, they were around for about 100 years. So very used by astronomers, but it's a bit tricky because you can imagine you sit there in the telescope steering hour after hour in the cold. Typically it's cold when it's clear, right? And you're capturing light on these glass plates. And if you steer incorrectly or it gets bad weather, well, then there is always tomorrow. So being an astronomer back then was really something about patience. You had to really spend a lot of time.
Very patient, and very cramped there. It looks very cramped.
Say again?
I said no. I was just saying it looks very cramped.
Yeah, cramped and very cold. And here is a famous astronomer. This is Annie Jump-Cannon measuring on glass plates. So she invented, in fact, the stellar classification. She found out that stars are sort of in groups, in families, and this was a really big jump in how we looked at the sky. But then around the 1970s, some clever people invented this fella here. So this was light sensitive integrated circuits, and we call them charge coupled detectors.
Charge coupled
charge coupled detectors. So these are light sensitive devices made of silicon. It's a bit funny and it looks a bit alien. So gone are those days where the astronomers looked through the telescopes and instead we use these kinds of chips, right? But those chips are in fact more familiar to us than most of us really know, because we have those kinds of chips. For instance, if you have a digital camera, then there is one of these charge coupled device thingies inside. We call them CCDs. And of course, we don't always know how these things work, like a digital camera. But also, again, we don't always know how a fridge really actually works in reality. We have these black boxes that we have around us. But inside, if you were to take it apart, there would be one of these chips. And also in pretty much everyone's pocket nowadays, you have a cell phone with a camera, and inside that camera is a tiny, tiny chip, which is this charge coupled device. So.
That's fascinating. Now, how does that work? How does that create the process of seeing? How does that work?
Yeah. So the thing is that the light comes in and hits this surface of metal, and then it creates a cascade of electrons, and you can imagine sort of a grid of pixels if you zoom in, and each of those then get a signal from the light. And if you kind of were to register the light, which is what the CCD does, and you kind of color in the amount of signal that comes, you can color in the numbers effectively, then you can see an image emerging. And that's exactly how those pictures are done. And it doesn't have to be just kind of black and white. You can also do it today in color, which is what happens in your cell phone in a split second. And astronomers, they took to this technology like wildfire, because you could register light very precisely and also very fast. And very soon, in the decades that followed, I think this photo is from around the year 2000, they made lots of them. They made them bigger, these CCDs, they put them together. So this one has about 100 million pixels and was sent up on a spacecraft called Kepler to take huge images of a big chunk of sky up in Cygnus to look for planets around other stars. And this is in fact the kind of technology which is up at Mauna Kea today. And they really drive a lot of modern astronomy. So with those CCDs, you can imagine sitting in the focal point of the big telescopes, you get the images down, and then the astronomers sit in the control rooms looking at the images and signals that are coming.
That's very nice. I like her sweater. Where's the romance there, though? It's got to be some romance, though, right?
Yeah, it's not like the good old days, right? Looking at the telescope. That's why many of us, like Jamaica and Rob on the call today, we still have telescopes. We still look at the stars, and I bet you many astronomers, they also occasionally turn off the light in the control room and roll up the blinds. And then they have a view like this, gobsmacking, right? Because you have that sky outside. Or you go out on the platform and look out in between exposures and look up at the sky. I know I've done that myself. So, but let's have a look at a galaxy. So this is one of my favorite galaxies, M83. It's a beautiful spiral galaxy, not totally unlike our own Milky Way. And imagine that you see this with the eyes from 1850. Then you make a drawing. This is a drawing of that object. And then if we slowly kind of move through time, if you imagine, to the invention of the photograph, the invention of the CCD, bigger and bigger telescopes, and you're able to take sharper and sharper images, then you can gradually see how the image of this beautiful object improves with time. And in fact, we're then up at the last image, which is kind of a modern day view. We just released this image from NOAA a few months ago. And this is kind of the edge of technology as it stands now. And you could see how the image became sharper, more and more light came. You can see hundreds of background galaxies. So the CCDs have really made a huge difference to astronomy. In some sense, that has been a revolution of technology. But there are other revolutions, and I want to talk about 3 of them today. And the first one was started around 1930-32 with the invention of the radio telescope. And it turns out that the part of light that we can see with our eyes, the colorful part here, the rainbow in the image, is a tiny sliver of the full picture of the spectrum. And people in the 1930s, they took these radio telescopes and looked out and found that the Milky Way is radiating in radio light. That was Karl Jansky from Bell telephone labs, as it was called back then, observing this radiation. So this opened up a new window on the universe. And up in then the 60s, people sent up sounding rockets which were above the atmosphere for just like a few minutes, and realized that there were in fact sources of X-ray light out there. And they saw things like neutron stars or black holes in just those minutes. And they also looked at a picture of the sun, for instance, or took kind of pictures of the sun. One of them I have here. This is from the 60s. And it was really opening, new eyes on the universe, the multi-wavelength universe, if you will. And we can try to take a journey through the multi-wavelength universe, starting with a view of our Milky Way. In fact, we're looking at the entire sky in this image, but the Milky Way is the dominant part in the middle. These are the stars in our vicinity around the sun. And maybe you can recognize some of the objects. We have the Pleiades. Also, we have the Orion Nebula over to the right, the constellation of Orion. We can also just have a look at the constellations that are. It looks a bit distorted because it is the full sky, all 88 constellations in one image. Anyway, we take a view of the sky now in just a sliver of the visible light in H-alpha light, which is hydrogen that's glowing. So this is a survey from WAM. It's a telescope. They all have different funny names at the Cerro Tololo Observatory of NOAA. And you see all these beautiful star-forming regions where stars are formed and they blow bubbles around them as they turn on with the bright blue light. We can go further out in the electromagnetic spectrum and look at the sky with infrared eyes. This is the 2-mass survey that was done at Cerro Tololo and Whipple Observatory. And you can here look through the gas that we saw before and look at the especially colder stars. And even colder stars and objects are seen in the next picture, which is the WISE satellite, a NASA infrared telescope launched in 2009, or in microwaves with the European Space Agency's Planck satellite that we can see in this view. Especially this view shows us the gas and dust in our Milky Way. Now people can model that gas and dust and in fact remove it. And that turns out to be even more profound in many ways. If you do that and remove those effects of our Milky Way, you get to this picture here, which shows you a relatively even surface of light out in the very distant universe. In fact, this is the end of the observable universe beyond the stars and galaxies that we've talked about so far. And we call it the microwave background. It's in fact only a few degrees above absolute zero, very, very cold radiation. But you can see that it's not completely smooth, right? So although I mentioned in the beginning that the universe was a soup back then, there is an imprint here of some fine structures, both dark and normal matter. So by analyzing this, and trust me, astronomers have analyzed this, you can get really interesting information about the universe we live in, how fast it expands, how much matter there is in it. So this is another way to see that there's all of this dark matter in the universe. Now, if we go the other way, to the harder radiation, we can look at the universe in gamma rays. This is the Department of Energy and NASA Fermi satellite looking at gamma rays. And these come from objects in our Milky Way. You can see the Milky Way in the center part of the image, but also behind you see these neutron stars and supermassive black holes and galaxies behind. So this is another way of getting information, looking at very hard radiation. Now, new technologies have then come up. So astronomers took the radio telescope up at Mauna Kea and combined it with telescopes in Antarctica, in Chile, in Europe, and elsewhere 2 years ago. And this gives an extreme precision because they could use the whole Earth as a telescope in a sense, and they created this picture that many of you may remember, the first image of a black hole. So that's really a way to get that kind of information and reach a precision that was not possible before. Now, the second revolution I want to talk about is the ability to look at the universe over time. And what you see here is a young star that has been observed over about a decade, and you can actually see the object move. You can see the gas flowing out of that object over time, which is, in a sense, a phenomenal discovery that the universe changes and that it happens on time scales that even us humans can see. It's not a static thing, but there's a lot of stuff going on in the universe. The third revolution is something even more alien, I would say, that it's not just light that is reaching us out from space. Also, neutrinos come from the sun. These are particles that we can't really see, or we have recently seen ripples in the fabric of space-time when black holes collide or neutron stars collide, and that emits gravitational waves that we can detect on Earth as tiny, tiny vibrations. So this is called the multi-messenger revolution. So the third of the revolutions that are happening at the moment. And we can put all these together, looking at the universe in different light, looking at the different messengers that come to us, and looking at the universe over time. And if we combine them, I would say that we are actually going to solve those three big problems that we asked at the very beginning. This is an image of a telescope of today, I would say. Actually, this was taken just yesterday on the 2nd of March, where the top ring of the Versii Rubin telescope was mounted. This is a telescope built by our National Science Foundation together with Department of Energy. And that is going to look at these changing phenomena. It is going to observe an image of the entire southern sky every 3 nights and create essentially what is a giant time-lapse movie of the southern sky. Every night there will be differences from the image before. So up to 10 million differences will be detected as kind of transients. These can be asteroids moving by, it can be exploding stars, it can be pulsating stars, it can be a whole variety of different phenomena that give so much insight into these three big questions. So this will be a whole new age for the dynamic universe or time domain astronomy, as we call it. And chances are that the really big discoveries will happen over the next decade with that big survey produced by the Rubin Observatory, combined with the multi-messenger observations I mentioned and the multi-wavelength observations. So a few words about Mauna Kea. It's really one of the best places in the world to do astronomy. There are like 2 that astronomers favor as the best. So Mauna Kea is the favorite location for the northern sky, and the northern parts of Chile is the favorite place for the southern sky. So they complement each other. And this photo was taken by Jason Chu. It's an amazing picture after a bit of snowfall on the summit, like happened also a few weeks back. It's not only above the atmosphere, poking out more than 4 kilometers above, or almost 14,000 feet, but it's also a very dry place, and it's clear up there and very, very dark. So of course, astronomers are honored to have the opportunity to conduct research at a place like this with such a significant role also for native Hawaiians, and amazing discoveries have been made up there. So if you remember, there was a Nobel Prize in 2011 given for the accelerating universe. And that discovery was partly done on Mauna Kea together with telescopes around the planet. And also last year, the Nobel Prize was given for observations of our center parts of the Milky Way, where there's a supermassive black hole 4 million times as heavy as the sun. And those observations were done in part on Mauna Kea by Andrea Guess and her crew, and then partly in Chile. This is really a profound discovery, and there's been tons of other examples of science done at Mauna Kea, images of solar systems around other stars, for instance, and many other things done with the Gemini North telescope and the other telescopes up there. So I think that we will, in the next decade or so, really get to solve those big questions, partly using the telescopes in Mauna Kea and partly in Chile, and try to uncover those hidden secrets of the universe that we posed. Where did we come from? What is the universe composed of, and are we alone? Thank you, and thanks to B93, B97, DC, and all our partners and sponsors.
Thank you, Lars. So thank you so much. Yeah, and everybody I guess the question that I want to ask, and really it's more of a playing devil's advocate here. We who go through our daily lives, why should we care about these amazing discoveries that are being taking place? All this, I mean, it sounds like we're on the verge, really, of a I think a golden era of watching things. Why should we care? Why should we care in our regular everyday life?
And that is such a good question, DC. And a lot of what we do is not it's not known why, right? We do things because of the curiosity of humans, because we're eager to uncover those fundamental questions. But for some of us, it's just not enough. And we have daily problems, especially right now, that are more important in many ways. And your question are well warranted, I would say. But the truth is that astronomy has led to some of these technologies that we use around us today. So the CCD is just one example of things that make life easier, but also the radio telescope I mentioned, right? Yeah, we have them, right? And the radio telescopes helped us to create the wireless technology that many of us are using right now on this call. And even things like sat navs in cars, they built on global positioning satellites, which in turn use a reference frame of distant quasars. So none of this would be possible without astronomy. And there are many other examples also in medicine. So it all goes together, I would say.
Yeah, I obviously, like I said, because even this, I mean, I just saw, those 100 megapixel processors, it's like, it is something that it does come down to us too. So thank you so much, Lars. Now, was there any questions? I know Alyssa you can't see her, but she's here. She's monitoring. Are there any questions that anybody asked? I mean, I've got a couple of questions I could throw at Lars, but if there's anything that somebody else would like to ask before we start our stargazing, now would be a great time for that. Hey, Lars, if you don't mind, I wouldn't mind asking a question here really fast. Back to the images. I've always wondered. The images are so beautiful, and how real are those shots? I mean, if we were able to go out into space and see, would it look like what we have, or do we need to see the full spectrum of color that we don't really have as humans? I mean, do they look like those pictures?
Yeah, that's another great question, and the answer is a bit complex, right? So the truth is that if you look at a nebula with a telescope and you go out in space, you wouldn't actually see a lot more than you see with your eyes from the ground, because you get closer, but also the nebula gets more tenuous as it gets bigger in the sky. The surface brightness is the same. So it wouldn't actually quite look like the images, but the images are also taken over long periods. That doesn't mean that they are not real. In fact, they are very real. The pictures are composed by different exposures through different filters. And in many ways, they go beyond what we can absorb with our eyes. So in a sense, the telescopes, they make things visible that we can't fathom or see with our eyes. But we always take care not to show things that are unreal, and we sort of stay very close to the scientific truth in a sense. But the truth is bigger than what our eyes can kind of grasp.
Lars?
That's the thing I'm fascinated about is,
Rob?
Go ahead. Right here. Is that Rob coming through?
Yeah, I was gonna say, could I promote our live from NOR Lab where we had Travis on recently?
Yeah.
Travis, right? We do a series called Live from NOR Lab on Wednesdays on YouTube. And recently we had Travis Rector, who does our astronomical image processing for NOR Lab, and he addressed this topic exactly what you're talking about. It's called Coloring the Universe. You can find it on our YouTube channel and watch the recording of the presentation there. He talks about exactly what you just asked about how the images are processed, how things would look like if we went there. So it's a great resource if you want to get a very detailed answer to that question.
Thank you so much, Rob. Appreciate that. Yeah, we'll definitely have to check that out. Well, Lars, thank you so much for your time. I really mean that, and it's so fascinating. And I might have to rewatch this later on just so I can absorb some of it. especially the whole messenger concept just blows my mind. Janice Harvey, I see you here. Did you want to jump in and say something?
Do I want to find out, from the audience, Alyssa, if you don't mind, if you could share some of the questions that possibly came in from the audience, I'd appreciate it. Lars, fantastic presentation. Even though I have been working at Gemini for 22 years, I am always fascinated to hear. I learned so much. And especially I've learned so much this week listening to the different astronomers and scientists. But tonight, wow, you did just blow my mind. DC, thank you again. Alyssa.
Aloha nui kako. Hello, everyone. My name is Alyssa Leinani Lozi. I'm joining you from Hilo, Hawaii, and I'm your moderator on YouTube. So that person messaging all of you right now, that's me. Thank you so much for saying hello, for joining us today. We have people from Memphis, Tennessee, and from different parts of California joining us tonight. So thank you, all of you, for being here. Yes, we do have quite a few questions coming in. And our first question from Nikki Thomas is, how is dark matter and dark energy measured?
Yeah, so I gave a hint with those distorted galaxies that is one of the ways that the dark matter is mapped. But also there was the image of the cosmic microwave background, which was this uniform yellow surface. And by looking at the structures in the distant universe, you can actually figure out pretty much all the parameters of the universe, how much matter there is, how much dark matter, how much dark energy, and how fast it's expanding. It's all connected, so it's not that easy, but through time, people have done different kinds of measurements. Very, very clever people, theoreticians, have modeled many things that they know about the very early phases of the universe when it expanded super fast. And in that sense, you can put it all together. And also, one last way of measuring is by looking at these supernovae, exploding stars. So if you measure them out in the universe at longer and longer distances, greater and greater distances, you can find out how fast the universe is expanding. And you can use them as a kind of a standard beacon as you go out in the universe, and thereby figure out the geometry of the universe and those kinds of things. And that gives us an indirect measure of the dark energy that is out there. That was the Nobel Prize in 2011. But it is far out stuff, and it is things that take very clever people very long to figure out little by little. That's why astronomers use time on telescopes like on Mauna Kea. That's why they go to conferences and talk and think and write scientific papers.
Well, it certainly sounds like not only a group effort, but a generational effort to figure out the answer to that question. Thank you for asking that, Nikki. Our next question is, can we see exoplanets with the telescopes on Mauna Kea?
And the answer is very easy. The answer is yes. It's a great question. Not only see them, but even families, so solar systems around other stars have been seen with the Gemini telescope, with the Keck telescopes up on Mauna Kea. It takes, again, a big effort, a group effort of engineers, of scientists and other people, because you need to remove the atmosphere above, or the effect of the atmosphere, by using lasers that create laser guide stars that you can then use as reference points, figure out how much the universe is flickering, and then using computers actually remove that effect. And that means you can take very, very sharp pictures of those solar systems around other stars. And that is one of the most profound things that we've seen. We can see other worlds out there and have imaged them from Mauna Kea.
Lars, may I jump in here, Alyssa, and say something real quick about exoplanets?
Jamika, you have the floor.
Excellent. Thank you so much, DC. Okay, so just a quick plug. I think tomorrow, Lars and Peter, we have a press release coming out about a new instrument we have on Gemini North that in fact does just that, looks for exoplanets. So they can, the general public can look for this press release tomorrow, correct, Peter?
Yeah, I think what you're talking about is an instrument called Maroon X. It's a great name for an instrument, and it's a spectrograph that can detect the velocity of stars. What happens is, as a planet is going around a star, the star actually wobbles a little bit. And so we can detect that motion with this spectrograph to a very high degree. In fact, we can detect it to about velocities of 1 foot per minute, which is about the velocity that the fastest tortoise on the Earth moves, to give you a sense of just how sensitive these instruments are and what they can detect.
Mahalo for that answer, everyone. Yes, what a great way also to highlight the teamwork of NORLab, that we have so many amazing people on this panel who are able to contribute to the answers to all your questions. Keep those questions coming, everybody. We have another one for you, Lars. This one is from Jovinda Govinda, and he would like to know what type of forces are coming from the cosmos onto Earth.
So there are 4 fundamental forces of nature, and the main one that really affects us on the scales of planets and stars is gravity. So that's the strongest force, and we can see the gravity in manifest itself in many ways. We can't see the gravity itself, but I would say that's probably the most prominent of them.
Okay, we hope that answered your question, Govinda. Our next question is, what are the first few scientific questions that will be investigated with the Rubin telescope?
Many questions at once will be investigated. There are hundreds of scientists eagerly awaiting those alerts as they are coming in. So it will be a whole host of things happening at the same time. It's a bit like, astronomy on Twitter in a sense, because of all these alerts that are coming out, and then all of the astronomers at the ready going to analyze the data and figure out all the things that are happening, everything from asteroids to exploding stars and dark matter and in between.
Mahalo. Well, that ends our questions for now. So on to you, DC.
Thank you so much. Thank you, Alyssa. Really appreciate it. Thanks so much for the great questions there too, audience. Is it too early? At this time, our next phase, I guess, is going to be some stargazing. And Jamaica Marshall is on the summit of Mauna Kea. We have Rob Sparks, who's in Tucson, Arizona. Are you folks ready? Are we ready to segue to that portion of our talk here this evening? If
Yes,
not, it's going to feel very awkward because I don't know what to.
Oh, sorry. Yes, DC,
Go right ahead.
I am here, and I believe Rob is also here. Rob, are you ready?
Yes, just about ready. I just woke up my camera to be sure that it would actually take a picture for us here. So that's you want to do, you're going to do your stuff first, though, right, Jamaica?
Yes, I'm going to start with our introduction here, and please confirm that you can see my video. Can you see my video?
I can
Yes,
see
we can.
Yes.
Okay, you can see me. Okay, fantastic, great. So I'm going to go ahead and share my screen here. Alyssa, can you see my screen journey through the universe?
Yes, we can.
Excellent. Thank you so much. All right. Hello, everyone. Again, my name is Jamika Marshall. I am an outreach assistant here at the International Gemini Observatory, which is a program of NSF's NORA Lab. And I am outside, so it's dark and you are unable to see me, but I can say I don't have any light to put on me. I will try to get that when Rob comes on screen real quick so y'all can see me. But in the meantime, a quick background here. Rob and I will be coming to you with some amazing images of our night sky. Now, Rob will introduce himself in a little bit and tell you where he's coming from. I am coming from not the summit, DC, but a few thousand feet below the summit. That is right here at the 9,200 foot level at the Visitor Information Station. If you've ever come up to the mountain and you are preparing to go to the summit, people typically acclimatize here. And I can say that right now we have people coming down the mountain from watching sunset. So if you see some headlights off to my left, I apologize for that, but that is because they're coming down from the summit. Really quickly, it is currently 36 degrees here at the visitor station, a lot cooler than it typically is in Hilo. And it's making my fingers a little cold, but you know what? I love being here. So let me quickly go into my setup. So what am I using? Well, I'm using three things here. First, Lars has already talked to us about charge coupled devices, CCD cameras, and I am using one myself. This is a GP CMOS series. This is a USB 2 guiding camera, and it fits into, it's a 1.25 inch and fits right into an eyepiece really easily. So that is the camera that I actually have already used for our images. And as I was sharing in the chat, one of the things you encounter doing astronomy outside is that you are subject to the weather. And while it is beautiful here, we have quite a bit of humidity and I'm getting condensation on my electronics. So I've covered the scope and thankfully I'll be using the images that I already have. Rob is not having such issues, no humidity, no condensation for Rob. So we will be able to view live sky with him. But my images are just from yesterday and the weekend. So I am excited to talk about those. And if this condensation stops, I will hopefully at the end be able to come back with my live view. In the meantime, let's go to the next piece of my equipment that I'm using, which is actually really important, and that is the telescope mount. Now I am using an Orion Atlas German equatorial mount. It is a computerized go-to telescope mount. I absolutely love this mount because it is really straightforward to use and easy to set up. Runs about the weight runs about 50 pounds or so. That's without the tripod. And last but not least is the actual telescope itself. I am actually using a Barska Magnus spotting scope. It's an 80 millimeter spotting scope, and it's one that's about just a little under 4 inches. And I have gotten some amazing views. And for some of my friends here in town who've done stargazing with me, they really enjoyed these images and the images that I can get with this refracting telescope. So how about I take it over to either Lars or Peter, and maybe you can tell us a little bit about what a refracting telescope is, because I believe Rob is actually using a different telescope.
Before you move on, Jamika, or before Lars or Peter answers that question, we do have a quick question for you from the chat. I think we're just going to ask the questions as they come in for this portion. And that question is, where in the universe are we looking tonight?
That's fantastic. Well, we are going to be looking first at, let me go up a little bit. We're going to start with Mars and the Pleiades. And so we're going to be looking, this is Rob. And so in the western sky, of course, we know the planets, everything rises in the east, sets in the west. And to catch Mars, we're going to start off looking at the west. And then he'll be followed by the Pleiades with that. We're also going to look at some galaxy and an open cluster and some globular clusters. So we have lots of amazing phenomena out in space to talk about. And so because Mars, I know, is pretty low on the horizon for Rob, let me go back a slide and let Rob do his quick intro, and then we will jump into Rob.
Okay, thank you. And you can stop sharing your screen so I can start sharing. There
Thank
we
you.
go. Perfect. That's wonderful. So let me go and share my screen. I actually literally just took pictures of my setup with my cell phone here.
Nice.
Let's see if I can find them so I can actually show them to you. Where the heck did they go? Where is my, oh, it's under there somewhere. I'm gonna have to move my window here so I can actually see it better. So where's that? There we go. That should do the trick. So let me get back to Zoom so I can share this screen and share the screen. Oh, it's still not sharing the screen I want. Oh, there it is. Okay, there we go. So I have two setups here, and this actually looks like a camera, and it is. This is a Canon 80D camera off the shelf with a Sigma 100 to 400 millimeter zoom lens on an Ioptron SkyGuider Pro, and that SkyGuider Pro tracks the stars, so it moves the camera so it tracks the stars. This is great for doing wide field photography. The main telescope I'm using can't see wide field like this, so you can only see the very narrow field. So things like Mars and the Pleiades, this is great for things like that, and I love this setup. It's very portable, easy to use, and I do a lot with the setup just like this. It's very, very fun and easy to set up. So that's what we're going to do with Mars and Pleiades. The other setup I have, let's see if I can actually make this go here. There we go. Yes, this is the second setup. Again, you're seeing my glorious townhome here, my glorious town outside my townhome, where literally just taken a few minutes ago, is an XStar 8-inch reflecting telescope, and it has a Canon 6D camera strapped to the back of it. And again, it's on an equatorial mount, and it tracks the stars, so we can see the stars as things go on, as nights go on, so we won't lose the view of the stars. And we can do longer exposures too. If you take a short exposure and a long exposure, you'll see the stars trailing as the scope stays still and the stars move. But to move the scope and the stars same speed, we can take longer exposures. So pretty much all telescopes do that. They track the stars. We're going to take any sort of timed exposure whatsoever right there. So that's actually my setup right there that I'm using, the two setups. And I'm going to go and get my other program that I'm going to use to, it says detecting camera, which is not a good sign. So let's see here. That means my camera went to sleep. I'm going to just wake up my camera again. It's got to push a button over here. Do anything to make the camera come out of sleep mode.
No problem.
Then I should be able to detect the camera and take a picture. So I actually am going to use Lightroom here to take a picture. Yep, it's detecting the camera because it's trying to download images, which is so with Lightroom, you can actually tether the camera and capture an image. So I'm going to start tethered capture right here, and up pops this little. Why is it doing that again to me here?
Oh, no.
Yes. Oh no, it detected. It's down there. 80D. That's good. I love this little capture bar down here. So if I push this button right here, it's going to take a 10-second exposure and show me Pleiades and the Mars. And actually, you're already seeing, because that's a previous picture I took a few minutes ago, a test shot of Pleiades and Mars too. They're fairly low in the sky right now, as Jamika said. And unfortunately, in the western sky, that's where my most light polluted part of the sky is. So we're seeing a lot of sky glow over there. But the nice thing about using Lightroom, and I didn't know you could do tethered capture in Lightroom until fairly recently, is that once they're in Lightroom, you have the pictures in Lightroom, so you can start doing some adjustments to them, some contrast adjustments and things like that, which if I do a contrast adjustment, maybe play with the black levels a little bit, I can start getting some of the that sky glow.
I don't think we can see that. We can see you, Rob. We can see you, Rob, but I don't think we can see your screen, though.
You can't see my screen? Okay, let me get this. Let me go back and make sure I got the screen sharing going on here. Okay, let's see.
You look great. I'm just saying. But yeah.
Thank you for letting me know. And
Thank you, DC.
there we go. Is that better? Now you can see my screen?
Yes.
Okay, so this picture I
here we
literally just took seconds ago. You can see my bar at the bottom here, Canon EOS 80D with the little bar here. I did a 10-second exposure, aperture of 6.3 and the ISO of 3200. So I can actually do pictures live and have them display fairly quickly here. We have Mars over here to the left, this sort of orangish object, and the familiar asterism of the Pleiades, which a lot of people, when I'm out doing star parties, say, hey, that's the Little Dipper. And well, no, it's not the Little Dipper, although it is in the shape of a dipper. It is in the shape of a Little Dipper. Little Dipper's in the north sky. It contains the northern star, the North Star, actually, Polaris. The Pleiades is even smaller. The Little Dipper, I call it the teeny tiny dipper sometimes, because the Little Dipper is even smaller than the Little Dipper. The Pleiades are only a very small object. If you go outside in hilo right now and find Mars, you can actually see both these objects naked eye, although you will see significantly more stars in this image than you will naked eye. And plus, this is zoomed in a bit, so you won't see as many stars as you will. You'll be much smaller in the skies compared to this right here. And like I said, I'm just moving a few things out here, and I'm gonna, play with a couple sliders here and see if I can actually make this look just a little bit nicer here. There we go. Get that sky glow suppressed a little bit, so it looks so we see the stars and less of that orange sky glow there.
That's
So it looks more like a dark sky now. It's one of those things you can do all these fun image processing things. Yes.
Rob, while you are doing that, I love that you are sharing your screen and showing us how you are using your image capture software. I will try to show mine on the next two slides. But in the meantime, can we have Alyssa? Alyssa, can you jump in and tell us a little bit about the Pleiades here with the Hawaiian Polynesian spin on it?
Sure thing, Jamaica. So, Rob, I love that you mentioned viewing it from hilo right now, because it is a rare, very clear night in hilo. So I think a lot of you, if you go outside and look towards the west, you'll be able to see the sparkly little cluster, which is known as the Pleiades, in Japanese known as Subaru, and in Hawaiian is known as the Makali'i. And so Makali'i has many different translations. One is the tiny eyes. And it's a really important little cluster of stars in Hawaiian culture because it actually helps to mark the start of the Hawaiian New Year. So right about the time that the Makali'i is rising in the east, when the sun is setting in the west, that is our first marker for the new year starting in Hawaii. The second marker, which you have to wait for after this event happens, is the next hilo moon phase. So the very first sliver of a crescent that happens after new moon is called the hilo moon. And once that happens, we are in the Hawaiian New Year. So that actually started in about November of 2020. So we got a head start on the new year last year, and it was terrific. Okay, we do have one question for you, Rob, in the chat before you go on, and that is, how much does a telescope like that cost?
I assume they're talking about the Celestron telescope. Is that correct?
I think so, yes.
Okay. Yeah, the 8-inch Celestron telescope. And again, you can get telescopes with a wide variety of price ranges. But this telescope, if I remember correctly, just for the telescope itself went for around $2,400-$2,500 roughly. But of course, there's a lot of accessories we added to it. We added a battery supply. We have extra eyepieces. We have the equatorial wedge, which lets us track the stars, do a polar alignment so we can track the stars for long exposure photography. So we spent a lot more than that on it because we did all the accessories to trick it out for photography and stuff, as well as some nice eyepieces for visual use as well. But of course, you can get scopes, if you just want a visible use scope, you can get them a lot less than that, or of course you can get scopes that are a lot bigger and spend a lot more than that. But this is pretty good. I like this setup. I like the 8-inch Celestron scope because it's big enough to see a lot and do a lot, but it's still fairly easy to tote around. If you get a really big scope, you have a very heavy thing you have to tote around and set up, which takes longer, and it gets harder on the back as you get older too. So,
if I can just add, this is Peter. You can also make telescopes too. It's a hobby for a lot of people, is building telescopes from the ground up, and so you can save some money that way too.
And of course, that doesn't include the camera either that I'm using. So, any other questions that you want to address quickly?
There is one question in the chat of what does hilo mean, and I can quickly answer that. It has many meanings. As a verb, it means to twist or braid. So it is one style of creating lei. Other meanings, of course, it's the name of one of the moon phases that I just talked about. And it's also the name of a ancient, very famous navigator. That's
Thank
all
you.
of our questions. Thank you.
That question I would have not known the answer to, so I'm glad you're here. So I'm going to mute out now so I can switch to the other, stop sharing screen and mute out so I can switch to the other telescope and get that camera set up and ready to go.
All right.
Okay, excellent. Thank you so
Fantastic.
much, Rob. I was able to grab a little bit of light, so now hopefully y'all can see me a little bit better now here outside at the 9,200 foot level here, the Visitor Information Station on Mauna Kea. Okay, Alyssa, Rob, thank you so much for that information on the Pleiades, also known as Subaru or Makali'i. I don't know if anyone in the audience has ever looked at the back of a Subaru vehicle, but next time take a look and you'll see that there are like 5 or 6 stars. And now you'll know that those stars represent the Subaru, or Pleiades or Makali'i. Thank you so much for that, Alyssa. And sorry, knocked my computer off. Okay, and so before we move on, if I could have someone, Peter or Lars, jump in and explain the differences really quickly between the 2 types of telescopes that Rob and I are using. Rob is using an 8-inch reflector, and I'm using a 4-inch or just about 80 millimeter refractor. Can someone explain that to our audience members for those who may not be aware of the differences?
Lars just sent me a message to ask me to do this, so I'm fine. Yeah, so Jamaica's using a refracting telescope, which uses a lens to bend the light, kind of like a pair of eyeglasses would, only a little bit more sophisticated. And like she said, it's a 3.1-inch lens that collects light. So if you could imagine that your eyeball was about a little over 3 inches in diameter, how many faint objects you'd be able to see if you could do that. Rob is using a reflecting telescope. Actually, it's I believe it's a catadioptic telescope, which uses a lens and a mirror, but primarily a mirror. And the mirror reflects the light. It has a shape like a bowl or concave. It curves inward. And so when the light hits it, it bounces off the mirror, and then it goes to another mirror and comes back to where the eyepiece is. And so it uses mirrors to focus the light or bring the light to a point so that you can view it with an eyepiece. And so those are the 2 main types of telescopes that we're using, and the 2 main types of telescopes that are available if you wanted to purchase a telescope to look at the sky.
Thank you so much, Peter. And yes, so this, I love using my refractor. It's definitely different than using reflectors, but I appreciate both types of telescopes. And before we move on from Mars and the Pleiades, of course, the Pleiades is a type of cluster of stars called an open cluster. Now, an open cluster is a group of young, very hot stars that are loosely bound together by gravity. And by young, typically we're talking about, less than 100,000 years old. Stars, of course, have very, very long lives. And so young is relative. Young is very relative. Our sun is about halfway through its life at about 4.5 billion years old. So these stars that we saw with Rob in the Pleiades, also known as Subaru or Makali'i, are much, much younger than that. Peter, do you have anything to add for us about open clusters?
Sure. Yeah, open clusters, if you could travel in time and go back several million years, you would see a cloud of gas and dust where the Pleiades are now. And over time, that gas and dust coalesces down into stars and presumably planets as well. And one of the objects that we'll look at, I think, a little bit later is the Orion Nebula. And it kind of represents the early stages of the formation of a cluster. And so if you could go forward a few million years or so and take a look where the Orion Nebula is in the sky, you'd see a cluster of stars there too. Stars tend to form in groups or in clusters. In fact, our sun is part of a cluster of, I think it's 7 or 8 stars, a very small cluster of 7 or 8 stars that include several of the stars in the Big Dipper, and so, or Ursa Major. And so clusters, things in the universe tend to clump together. And it's a good example of how in star formation, it tends to happen in groups and communities of stars.
Thank you so much for that, Peter. Okay, so we're actually going to now move on. Peter was talking about where stars are formed. So we are segueing in from young stars to see where these stars are formed. And here we are at M42. Please confirm that you can see my shared screen. Thank you, BC.
We see it. Looks
awesome. Thank you. Thank you. So the Orion Nebula is also known as M42 for those of you who know your Messier numbers and maybe are familiar with that catalog. The Orion Nebula is one of the closest star forming regions to us. And here is one of my images, one of my more recent images that I got of the Orion Nebula. And right now, I'm trying to do some processing to make this a little bit clearer. It's a bit hazy, and I had some condensation earlier right now, actually, on my lens. And so I'm using my backup image right now. Hopefully, I can come back with a clearer view. But here, you can see that it looks very wispy, and you have what looks like some bright stars kind of right inside of there. The Orion Nebula is a molecular cloud, also known as a stellar nursery. Lars or Peter, would you like to jump in and talk to us about what exactly is a molecular cloud or stellar nursery?
I'm happy to.
Thank you, Peter.
Yeah, so it's essentially a cloud mostly of hydrogen gas, and that hydrogen gas over time, like I said when I was talking about the Pleiades, coalesces together to form stars. It forms into clumps, and then those clumps get bigger, and gravity takes over and starts to collect more and more of the material together to coalesce into stars. And once enough of that material collects together, the pressures get very, very great in the center of those young stars, and you begin to get nuclear reactions, and it begins generating energy and begins to shine. And that's what you're seeing there, is you're seeing some of those young stars starting to shine in the Orion Nebula, and telescopes like Gemini and others around the world have studied those regions in great detail. So that we can see that process happening. It happens very, very slowly. And so, if we look at that happening in the Orion Nebula, and then we look at it happening in other nebulae in the sky, we can sort of piece together a coherent story about how stars coalesce together by looking at them at different stages of formation, like in the Orion Nebula and other, there are clouds like this all over the sky. The Orion Nebula is just the closest and brightest one that we can study in great detail.
Yes, thank you for that explanation, Peter. Okay, so just in case some of you may be unfamiliar with this M number and whatever that is, M here for M42 stands for Messier, Messier. And the Messier catalog was started by Charles Messier. He was a French comet hunter, and this is back hundreds of years ago. Maybe someone can grab the date and maybe put it in the YouTube chat. I apologize, I don't remember exactly the dates, but he was a French comet hunter. And now he's looking for comets. This was the thing that people with money would do. They would have people over to their homes, show off their telescopes, and you come and you have a star tour. Well, Charles Messier kept coming across these objects that he called fuzzy wuzzies. What are these things? They're clearly not comets, but they're in his field of view. So he started making a list of these objects so he would know that they are not comets. Now, he didn't necessarily think of this list as something significant, but we now know that so many of those objects from Messier's catalog are, yes, they're fuzzy wuzzies, and it turns out those fuzzy wuzzies are things like the Orion Nebula, stellar nursery, or they're galaxies like something that Rob is going to show us very soon, or globular clusters, or even planetary nebulae or supernova remnants. So that is what this M in 42 means. It is the 42nd object on Charles Messier list. And I see Alyssa Leinani, do you have questions for us before we move on to Rob's next object?
Yes, we do. From our YouTube audience, the question is, do stars in nebula have planets?
Ooh, Peter, Lars, take that one.
Yeah, I'm not touching that one.
Me either.
I'm sorry, I missed part of that. Do stars in nebulae have planets? Was that the question?
That's correct.
Okay. Quite likely they do. Typically when we're looking at stars and nebulae like this, and they're very young, and so a lot of the exoplanets that we look at around other stars are very young because they're still very warm, and we typically look at them in the infrared or heat radiation from space. And so when we look at just general stars out there in space, majority of them have planets. And so it seems that planets are very, very common. So it would be, I think, unlikely that there are no planets around these stars that we're seeing in some of these nebulae. However, they're very, very young and very hot planets. And so they might be the type that we try to detect with our telescopes in the infrared, or heat radiation from space.
Yeah, and I can mention also the Orion Nebula is quite famous for having a series of very young planetary systems. But I should say, you can only see the dust and gas disk around those newborn stars. And it seems that they haven't had time yet to form real solar systems with condensed planets as such.
Awesome. Thank you so much for that question, Leinani, and for that response, Peter and Lars. Much appreciated. Okay, Rob, are you ready for your next object?
I sure am, and I'm going to go to share. Whoops, I need you to stop sharing screen so I can.
Yeah, right.
Okay, so now I will. Now I've got to find my Lightroom one. Yes, here it is. So, okay, should be able to see my Lightroom screen here. It says no photos selected. I'm going to take a 30-second exposure this time, a little bit longer. This is another open cluster called M46, that Messier object. I'll start the exposure here. I'm taking the longer exposure because this cluster has a little surprise in it if you take a longer exposure, which makes it one of my favorite objects in the sky. Now, this cluster is a much denser cluster than the Pleiades. You will need binoculars to see it. But it has a lot more stars much close together, so it's probably a younger cluster. The stars have not had as much time to spread out yet, but we should be getting just about to the time where this should be just about done with the exposure, because we will see the nice dense cluster and hopefully be able to pick out a small little surprise in this as well. Oh, I heard that click, so that exposure is finished. And yes, here it is. So we have a very nice dense cluster here, and this is also getting lower in the sky, so it's a little bit darker than it was earlier. So I don't see it quite as well as I did earlier because we got a little bit more light pollution in this part of the sky. So I'll just sort of slowly make a couple adjustments here to try and bring out this a little bit more here. But this nice dense cluster of stars, and this little surprise I have here. Let's see if I can just do a little bit more here, maybe make the blacks a little bit less. Yeah, there we go. Starting to get that down here a little bit. This little surprise here is that little blue circle there. There's a little blue circle right about here. Little blue guy right there. And I'm going to zoom in on it for you. That is a planetary nebula. So that is a star that actually has ended its life, a star about the mass of our sun. I think someone mentioned planetary nebulas earlier. after it's exhausted its fuel and spewed off its atmosphere. Its outer layers of the atmosphere is spewed out in this little cloud of gas and dust that surrounds the dead star. The center of the sun is a white dwarf. I don't think we can see the white dwarf. This is too faint. I think it's just a foreground or background star. It happens to be at the center of that nebula. But it's one of my favorite objects because of that little nebula. And that nebula is probably not actually part of the cluster. It's probably either a foreground object, either closer to us or farther from than us. I can't remember if it's closer or farther, if they've determined that with this particular object. But I just love that little object because it has that little thing in there. And yes, if you have a telescope, through this 8-inch telescope with an eyepiece, you can see this beautiful star cluster, and you see that little hazy gray nebula in there as well. So it's one of my favorite objects to observe visually as well as photographically here.
Okay, we have a
Rob.
question from the chat for you, Rob.
Yes.
How far away are we from this star cluster?
Oh, that's a great question. I would actually have to look it up. I do not know off the top of my head, but your typical open clusters in the order of a couple thousand to light years away, a few hundred to a few thousand light years away. They're not halfway visible from the other side of the galaxy in a telescope of this size. So this is probably on the order of 1,000 or 2 light years away, but I'd have to look it up to be exactly sure how far away it is. If someone has looked it up or is Googling it and wants to chime in with the distance, please feel free.
Yes, it looks like Lars just dropped it in the chat for us, and I was just about to say it's about 4.9 thousand light years away, 5,000 light years away. And maybe, Lars, could you tell us how we get these distances to such far away objects?
Yeah, it's a really good question because as we've talked about, we only get the light from the stars. We can't really, put out a measuring rod and measure the distance to the objects or their sizes, right? So you can imagine if you see the headlights of a car, then because you know that the headlights of a car are maybe spaced 6 feet or something like that, then you can deduce how far away a car is. And you can use the same kind of methods when you look out at objects in the distant universe, but you need some of those parameters fixed. And for open star clusters, the really cool thing is, and admittedly, astronomers can be happy about very small things, but the very cool thing is that we know they were born at the same time. So that kind of fixes one of those parameters, which is their age. And then you can start deducing things like distance and other parameters.
Okay, speaking of distances, maybe Lars, you want to add on to your answer here. Another question is, how far is a light year?
Yeah, it's a good one. It's really, really far. It's a distance that light moves in a year. So it's 1 followed by 13 zeros kilometers. So really, really far.
And if you consider that light travels 186,000 miles every second, consider how far that would be if you had a whole year for that light to travel. And a light year in astronomical terms is relatively close. The closest star to us other than the sun is 3.4 light years away. Our sun is about 8 light minutes away, just to give you a sense of some of the distances in terms of measuring by the speed of light.
Also 6 trillion miles for those that are on the British side of the British imperial unit side of the pond, which is 6 followed by 12 zeros. So
Love it. This is amazing, Rob. Thank you so much. And before we move from this, I'd like to talk a little bit about planetary nebulae really quickly, because I believe people are familiar with, or at least have probably heard of, supernovae or supernova remnant, but maybe they don't know what a planetary nebula is. And now let me give you a hint. No has nothing to do with planets. I know that's super confusing, but planetary nebulae are formed when stars like the size, like our sun, stars that are typically less than 10 solar masses when they end their lives. And so what you have is at the end of their lives, when they're finishing converting hydrogen to helium and are no longer a main sequence star, they will start to give off their outer layers of gas and dust, which makes them start to have different sizes. They vary that size. And that gas and dust that's given off finally at the end of its life will be what remains, that planetary nebula. Lars, Peter, would you like to add anything to that explanation of planetary nebula before we move to my next object?
Just
I think
that
you did very well.
if you stick around for about 4.5 billion years, you can see one up close and personal.
The sun.
I would just also add that these are temporary objects. They're very short-lived, on the order of 50,000 years or so. As the gas spreads out, it becomes dimmer and fades from view. So these objects don't live long in the cosmic scheme of things, because 50,000 years is considered fairly short when stars live for millions or billions of years.
Absolutely. Good point, Rob. And I didn't realize that they were so short-lived, relatively so. All right. Thank you so much, Rob. Amazing. I will now share my screen.
I'm going to mute out and get my next object centered.
Excellent. And I am going to share my screen. And hopefully you can all see my image of Omega Centauri. Rob and I actually both had backup images of Omega Cyn, and I had to decide which one to use, and I went with mine. I know it's not super clear, but I love this, and I'm having fun with this new CCD camera, y'all. I really have only been using it for within the past month. So really new for me to do. And I'm happy to share these images with you. And I apologize that it's not super clear. But again, I'm using a 4-inch scope, and it really does highlight some of the differences. The larger your aperture of telescope, the more light, of course, you can gather, which means the fainter the objects that you can see. Okay, before I continue, I see Leilani there. Leilani, do you have a question for us?
We have a couple of questions in the chat, but I actually wanted to point out that we are at our planned ending time for this event. It flew by very quickly. We're all having a lot of fun here, I think. I did also want to check in with DC and see how he's doing. We have all of our sciencey staff getting all excited about the stars, and I just wanted to see what DC thinks of all these amazing pictures. Yes, mind blown. DC, do you have any comments for us?
Well, I'm just so fascinated with the technology and just what we're able to do with this technology, what we're able to see. And, the more we learn about our universe and how it works and how, it makes us feel a little bit insignificant, but in a way, I think it makes us feel a little bit humble too. The beauty of the universe. And I'm enjoying this. I'm just a spectator here and enjoying this very much.
And this is Janice, if I can join in too for just a moment. So DC, isn't it amazing that so many of these images and what we can see from our own backyard up on Mauna Kea? Isn't it just amazing what these telescopes are capable of doing? And as Lars was speaking earlier, what are we going to find in the next decade? That's, what this entire presentation was about tonight was the next decade of possibilities. So I think that we have such a treasure on this big island, with the telescopes up there on Mauna Kea. And yes, everyone, this was to end at 8:30. So we're a little bit over time. I know DC has a program that starts early tomorrow morning. And DC, we just want to say how much we appreciate you. Thank you so much for joining us. But I can also say if we wanted to stay on for maybe 10 minutes more, possibly, if no one has any objections, can we go ahead and do that? Okay, so how about we give it 10 minutes more? Take it away, Jamaica and Rob.
Okay, thank you so much for that, Janice. Thank you so much, Leilani, for that heads up about the time. Apologies that we're going over. So for those of you staying with us in the YouTube audience, thank you, thank you, thank you. Okay, quickly, because we just have 2 more objects after this. Omega Centauri, also known as NGC 5139, that's another catalog name, is an amazing globular cluster. Now, globular clusters are, I think, my favorite objects to look at, because when I imagine what a starburst would look like, it wasn't quite like an open cluster. But when I saw globular clusters, that was it. Globular clusters are groups of very old stars that are tightly bound together by gravity. And unlike open clusters that orbit within the plane of our Milky Way, the globular clusters actually orbit above and below the halo of our galaxy. And specifically, Omega Centauri is it's really interesting. It's thought to be the core, actually, of potentially a dwarf galaxy that our galaxy, the Milky Way, just kind of grabbed. Lars or Peter, would you care to elaborate a little bit more on globular clusters really quickly and Omega Centauri?
Yeah, I'm not sure if Lars is still with us. He might have gone back to bed.
No, I'm still here.
Oh, you are there. Okay, I don't see you on there. Lars, do you want to say anything more?
Yeah, sure. So the globulars is another great case. So these are among the oldest objects in the universe. Again, their origin is a little bit still shrouded in mystery, but we know that the globular clusters are born as some of the first objects, maybe at the same time, roughly, as the galaxies are themselves in which they live. They orbit around the galaxies, and also, like the open clusters, have the same age. So that's again an example of how you can use that to fix some of the parameters to figure out the physics of the stars in them.
I might just also add that Omega Centauri is well, it's the brightest globular cluster in the sky. It can be seen with the naked eye. However, from the northern hemisphere, it's a little bit challenging sometimes to see because it's fairly deep in the southern sky. And that's one of the reasons why having telescopes on Mauna Kea, having telescopes in Chile, complement each other very well, because from Chile, it would be much higher in the sky and you'd get an even clearer view of it. You'd be able to study even more detail in Omega Centauri because of its location in the sky.
Awesome. Thank you so much, Peter and Lars. Rob, are you ready for your final object of the evening?
Yes, I am. So I will share screen if you let me. Thank you very much. Let me find my Lightroom here. So my final object of the evening is M82. It's a galaxy in Ursa Major, so it's a good northern hemisphere object. And again, I'm doing a 30-second exposure because it is a galaxy. It's, if I remember correctly, 10 million-ish light years away, 10, 11 million, somewhere in there. So it's a fairly, good distant galaxy, not really distant in terms of our what we consider distant in astronomy, but 10 million light years, we're seeing as it looked 10 million years ago, as Lars talked about. That's how long light takes to get to us. And this is sometimes called the exploding galaxy or the cigar galaxy. It's a starburst galaxy. It recently underwent an interaction with another galaxy called M81, which is not going to be in the picture. This camera doesn't quite show a big enough field of view to see them both. And did I just hear it go? Oh, I think I just don't know why it didn't show a picture there, but we'll have to see. Did it show a picture? I just didn't select it. Oh, that's the previous picture I took, the test shot. That's only 10-second exposure. Let's see if it does a... Yep, the camera's exposing, so hopefully the picture will come up in just a few seconds here. Whereas I talk about the galaxy, yes. So it interacted with M81, and we can't see M81 in this picture because it's just outside the field of view. I can barely get them in the field of view at one time. They're both way at the edge, and they both look bad. So I'd rather show you one good galaxy than two bad galaxies. And I think this one is the prettier of the two, the more interesting of the two, so I chose to do M82. And why are we not getting a picture? There we go. There, downloaded. Perfect. Yes. So now we got it here. So here's our galaxy M82 here. I can zoom in a little bit on it, and I can adjust contrast and play with the images and stuff there. And we start seeing a little detail in the galaxy there as well. So we can see some of the starburst regions in the galaxy there. I'll just Oh, there we go. That's starting to get some good contrast there. And see a little dust lane. Looks like we have a dust lane that's sort of bisecting the center of the galaxy here. So we see all kinds of detail in there, which is a very nice image of that galaxy there for a quick and dirty 30-second exposure, to say the least. Obviously, to get really good images of stars, we'll take either longer exposures or we'll take lots of short exposures and stack them to reduce the noise and stuff like that. But there's only one exposure. I don't have time to take dozens of exposures here for you and stack them to get a nice clean image for you. But there's a very nice little starburst galaxy here, we call it, because that's currently undergoing a burst of star formation. Our galaxy, the Milky Way, doesn't have a lot of supernova in it, but this galaxy, we've seen multiple supernova in it. And I actually photographed one. I think it was 2013-ish, 2014, somewhere in there. There was a supernova in here. And I photographed it, not with a telescope, but with my camera and a zoom lens on that Ioptron Skyguider Pro I showed earlier that I used for the Pleiades. So even with this fairly small thing like that, the supernova is just this little bright object that appeared in this galaxy for several months and then slowly faded from view. So that's a fun thing to do, is photograph a supernova here. Because it's a starburst galaxy, has a lot of stars forming, it's going to have a lot more supernova than most galaxies like our Milky Way. Do you have any questions or comments that Lars or Peter would like to add about M82?
Just one observation that is pretty easy to make from this image. That's a nice job, Rob, getting that image. But you can also see some dusty areas too. It looks like there's sort of some dark areas and dark zones in there. Mm-hmm. And that's where there's some obscuring dust in the way, blocking our view of the
I've got one about right here and one sort of across the middle here. So we got to have some dust lanes in there we can see.
Yeah, and it's a cool example of a galaxy undergoing a collision or having undergone a collision with another galaxy recently. And that really triggers a lot of activity in a galaxy. So new stars are formed, and as you say, supernovae go off. These are the short-lived stars, the big stars that explode relatively soon after a collision with another galaxy or a near encounter. And when we say short, it's a few million years, which in astronomical terms is a short while.
I think one of the things that you can lose sight of when you're looking at an image like this of a galaxy is that what you're looking at there are billions of stars in one big star city. It's just so far away that we can't resolve all the individual stars in there. And we're seeing sort of the larger scale structures in there. But really, if you could zoom in and get a closer look, you'd see that it was made up of literally billions of stars.
This is an amazing image, Rob. I absolutely love it. And yes, when if anyone is looking at the night sky, looking up at the Milky Way, you will also see some dark, patchy areas that is gas and dust, just like we're seeing here in the Cigar Galaxy, also known as Messier 82, just like this galaxy, because you'll find that is a characteristic of all galaxies, having this gas and dust there. Thank you so much, Rob. And we're at our time here, but I think I can squeeze our last image in just a minute, really quickly. I'm going to share my screen. And our last image is actually from the Gemini Cloud Cam from the other day. And I put the name up here. I meant to ask the audience if they recognize this. This is, again, one of the many things one of the objects that you are unable to see from the mainland, and that is Crux and Alpha and Beta Centauri. Crux is the Southern Cross. Let me move my cursor right here. Now, we do have a Northern Cross that's in the summer triangle, but and we also have a false cross, but this is not the false cross or Cygnus, which is part of, you can see the Northern Cross. This is the Southern Cross. And over here, these two stars are Alpha and Beta Centauri. And I believe Peter mentioned earlier Proxima Centauri, and that is the closest star to us. The closest star system is the Proxima Centauri system. And I believe Leinani is going to talk to us a little bit quickly about the Hawaiian and Polynesian mythos around Alpha and Beta Centauri and Crux. Alyssa.
Okay, so I love this picture that you've chosen, actually, Jamika, because I think that what we're looking at, and correct me if I'm wrong, this is the true summit of Mauna Kea. Am I right?
Yes, I believe so. Peter? This is, I think, our west. This is our southern camera. I believe so. Yeah, this should
Yeah,
be
that's
the
correct.
actual summit.
That's the view looking due south from Gemini.
All right, thank you. Yes, I don't get to go up to the summit very often, so I wanted to be sure that I'm recognizing it correctly. So what we're looking at is the true summit of Mauna Kea. Of course, the Mauna Kea observatories are near the summit area, but this pu'u here, this point, is the actual summit. And so really beautiful shot to have the Southern Cross, or in Hawaiian, it's called the Hanai Kamalama. Sorry, I have to learn to pronounce that a bit better. And it is a really important constellation for Polynesian navigation. So it's a part of one of the 4 major Hawaiian star lines. It's a part of Iwi Kuamo'o, which is known as like the backbone or the backbone of the lizard, but also thought to have genealogical metaphors there. And right next to it, I think you called it the point. Did you call it the pointers, Jamika? In Hawaiian, it is called the pointers because they point towards the Southern Cross. And it's just, the other amazing thing about this constellation is that it kind of marks where Hawaii is latitude-wise. So the distance between the top and bottom star of the cross is actually equal to the distance between the bottom star and the horizon. So when you're sailing out in the ocean, not only can you use the North Star to determine your latitude, but you can also look towards the Southern Cross to see how close you're getting to Hawaii. Now, before you move on or talk more about this amazing picture, we do have some comments from the chat that I think you would enjoy. So we have a local teacher who joined us for a lot of our Journey Through the Universe live education events this week, who said that Omega Centauri is her favorite object to look at through telescope. So I thought it was really fun that you had mentioned it's also one of your favorites. We have a lot of thank yous to everyone here for hosting this event. And we have Connie Walker, one of our colleagues, who wanted to mention that the previous galaxy displays a lot of hot winds that are flowing out great distances perpendicular to the disk. It is also known as an irregular galaxy because it does not necessarily have a spiral structure like our galaxy.
Yes, thank you so much for that.
I want to thank everybody for joining us tonight. What an incredible presentation. Lars, we can't thank you enough. Again, I think that everyone, the entire audience that joined us tonight, learned so much. And DC, I'm going to turn this over to you. Again, we thank you. We thank your radio station. We thank, oh my gosh, thank you everybody who joined in the conversation tonight. If you're sitting out in the audience, I think that, boy, did you learn a lot tonight. I learned a lot tonight from everybody as well. Thank you, Rob, for joining us from Tucson, Jamaica, from up at the summit. Oh, and Leilani, that's hard for me to call you that because I'm so used to Alyssa, but I'm going to do it. Your knowledge, you know, your Hawaiian knowledge, I think that's so special for this audience. So again, thank you for sharing that. Peter, oh my gosh, your knowledge just always knocks my socks off. So Joy, thank you for taking the photos. And DC, again, thank you, radio station. Thank Chris for allowing us to do this. Thank you for being our moderator. I hope we get to do this again at another time. We so appreciate everybody.
Game.
Yeah, I'm turning it over to you to close the show.
Oh, well, thank you. Thank you very much, Janice. Indeed, I will pass that on to Chris and the rest of our staff here. Thank you, everyone. Jamika, Peter, Lars, Leilani, Rob, thank you as well. It was a pleasure to talk to all of you. And I guess we're going to go ahead and just wrap up our Journey Through the Universe talk and just say a great big mahalo to everyone who's watching. And thanks so much for the questions. So please drive safe. Jamika, drive safe down the mountain. Rob, you drive safe going home. Lars, have a great day because it's the beginning of his day. Peter, you take care. Our friends and neighbors right here. Hilo, you, of course, Janice. Thank you so much, everyone. Have a great night, and hopefully we'll talk to you again soon.
Thank you.
Aloha, everyone.
Bye, everyone.
Aloha.
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 Good night.